Hello everyone, my name is Qinyang Shou. I'm from University of Southern California. Today I'm going to talk about my work of measuring spinal cord blood flow with multi-delay Picasso. I have nothing to disclose. Spinal cord is part of our central nervous system. It can be divided into four parts: the cervical, thoracic, lumbar, and the sacral spinal cord. It is important to know the blood supply of the spinal cord. The main blood supply of the spinal cord is from segmental branches of large arteries. For example, the blood supply of the upper part of the cervical spinal cord is from segmental branches of the vertebral arteries. Arterial spin labeling has been widely used in the brain perfusion imaging. It can quantify the blood flow but will suffer from low SNR. In this study, we focus on the cervical spinal cord. This figure shows the imaging slab and the labeling plane of our image, and the phase contrast image and the block simulation shows it is feasible to label at this position, with a slightly lower labeling efficiency compared to the brain ASL because of lower velocity in the vertebral artery. The cerebrospinal fluid, or CSF, is one of the problems in imaging the spinal cord perfusion, since it exists around the spinal cord and is also flowing at a low speed, which will cause signal fluctuation. Background suppression is recommended in ASL application of the brain, and in the brain we usually want to suppress the tissue signal, which is gray and white matter. However, in the spinal cord, CSF is the main concern, and thus we want to use two unconstrained inversion pulses and optimize their timing to suppress CSF signal. This figure shows the image before and after applying the background suppression. We can see that by applying the background suppression, we can suppress the CSF signal by about 95%. So next I'm going to introduce our experiment. In our first experiment, we used a high-resolution protocol with resolution of 2 mm isotropic and 4-segment readout. The matrix size is 96 by 96. TR is about 4 seconds and TE is 30 milliseconds. The labeling duration is 1.5 seconds, and 10 delays ranging from 700 to 2300 with an interval of 200 milliseconds were used with 2 averages for each PLD. The scan time for the ASL is about 10 minutes, and the total scan time is about 40 minutes including structural scan and the diffusion scan. All ASL images were interpolated to help draw RI in the spinal cord. The RIs were drawn manually on the average control image. This figure shows the typical image in the 3 planes overlaid by the spinal cord ROI. Here are the results. This figure shows the images of the spinal cord from different protocols. We can see that the T1 structural image can get a clear contour, the diffusion-weighted image can show better gray and white matter contrast, and the fitted spinal cord blood flow map showed higher signal in the middle of the spinal cord, which is likely to be the gray matter. And here is the multi-delay perfusion signal curve of the 10 PLDs averaged across 5 subjects. This curve showed a 2-peak pattern, which may be related to the 2 sources of blood supply. And this is the fitted spinal cord blood flow and ATT values of the 5 subjects. The values are comparable to the white matters in the brain. However, we think this 2-peak signal may be caused by too few averages and low SNR, so we conducted the second experiment to validate the results. In experiment 2, we used a slightly different protocol with larger slice thickness and less slice. We also reduced the number of PLDs to have more averages for each, and we also used the sense acceleration factor in the phase encoding direction. The total scan time is about the same as experiment 1, but we can get higher SNR. We collected data from 3 subjects with optimized protocol, and the results showed only 1 peak at around a second. We think this result is more reliable as we also found a similar pattern of perfusion signal in the vertebral arteries, which may suggest a source of blood supply in the spinal cord. In this study, there are still some improvements need to be made. First, higher resolution is needed given the small size of the spinal cord, and since the signal is low, we want to try some denoising method to improve SNR. In conclusion, it is feasible to measure spinal cord blood flow with optimized multi-delay arterial spin labeling technique, and the measured perfusion signal level in the spinal cord is close to the value between gray and white matter in the brain. Thanks for your attention.